types of mobile robotics, or how do we classify them broadly. Then we'll quickly go into the application and use cases where these mobile robotics or mobile robots basically find their major use case. From there on, we'll understand from a system point of view what are the different components, basically, or hardware and software components that would basically make up such a mobile robot. And from there on, we'll touch upon some of the key software components like the navigation, path planning, localization in the vision system, and the fleet management system, which is again one of the very important software module in mobile robotics domain. After that, going forward, we'll touch upon the simulation, how simulation plays a role basically in the mobile robotics development. And at the end, we'll go to future developments or what are the challenges that we see when we are basically working with mobile robots or deploying mobile robots. So first thing, introduction to mobile robots. So basically mobile robots would be some intelligent vehicles which have the ability to move autonomously. So for moving autonomously, they would basically require sensors such that they can perceive the environment around themselves, right? And once they have perceived the environment, once they understand the scene around themselves, they can basically, so to say, react and take decisions to move in that environment. So that is, so to sum up, mobile robotics would be these intelligent vehicles which using the source data or the input data would make decisions and navigate in a given environment to basically complete a set of tasks. So I'll come to the application and use cases. But before going into that, I'd like to explain why mobile robotics. So there's a lot of work that has, if we look at the warehouse automation, there's a lot of manual work that has been done. So mobile robots would help there to basically perform those tasks. So tasks such as lifting task or transfer of material from one position to the other in a warehouse or in a distribution center, such that the efficiency can be achieved. So basically we want to achieve higher throughputs. We want to ensure that the safety is at the prime. That means we want to ensure that when these operations are carried out, they are carried out in a safe manner, because these robots would be working in a collaborative environment along with the humans. So that is why the safety becomes a very prime thing. The third thing would be the scalability. So yes, mobile robots provide us the opportunity to scale the, so to say, scale the setup, right? And the last thing, which is very important, is the flexibility. So basically, the mobile robots are flexible to any kind of changing environments or locations, which would be, which is basically one of the major advantage over the conventional methods such as conveyors. So in warehouse distribution centers, a lot of material transfer currently happens with the conventional systems like conveyors, and this can then be very easily made flexible using the mobile robots, right? So some of the technologies in order to make this happen, in order to make this automation system successful, like I mentioned, the mobile robots have sensors. So some of the technologies that would go into such a mobile robot would basically be the localization system. So the localization system helps the robot to tell where exactly it is in the warehouse and where it has to go. The second is the sensor and the perception system. So basically, not just navigating from point A to point B is important, but also to identify different obstacles that might be on the way. That is basically captured by the sensor and the perception system. The actuators and the navigation system, the third point, would then basically ensure that the route I take from going from point A to point B is first of all optimal. It is efficient in terms of the traffic or the travel time, and the actuators should then be able to basically achieve those commands such that the robot can move on that path, right? And the last major technology that comes into the mobile robot, one of the major things is the fleet management system. So in general, such mobile robots, when they are deployed in a warehouse or a distribution system, they would basically be working in bunch of bigger numbers. So let's say 20 robots or 50 robots. So in that case, it becomes very important to have a fleet management system which is able to plan cooperatively for all these agents, such that the overall throughput of the system or the overall efficiency of the robots is basically increased. So now going on to the classification. So I mentioned why mobile robots and what mobile robots would basically do. But even in the mobile robotic field, we have different kind of technologies, right? So first I'll come to the AGV, which we call as the automated guided vehicle. So in the AGV field, as the name suggests, they are basically they are more guided mobile robots, which would travel on a predefined path. So this predefined path could either come from a guidance system such as fleet management system, FMS, or it could be a set of localization or ground markers such as magnetic tapes, barcodes, RFID technology, right? Um, so where would basically the AGVs be used more is where we have repetitive tasks, right? Since the magnetic tapes, for example, the barcodes or the RFID in a given warehouse would be basically laid. This makes the AGV, so to say, more suitable for repetitive tasks and an inflexible environment. So when I say inflexible, it doesn't mean it is not scalable. Inflexible only means that the AGV would be moving along such markers, right? And they're mostly used when the tasks are repetitive and the efficiency or the speed that is required is very high. So that is the AGV. Now coming on to the AMR. So in contrast to AGV, AMR are basically, so to say, more intelligent vehicles, right, which have multiple of sensors. So these multiple of sensors could include sensors like camera, lidar, ultrasonic, which help the vehicle basically perceive the environment around itself. It is able to localize itself using the technologies of SLAM, which is simultaneous localization and mapping. And once it knows where it is in a given environment, it is able to basically go from one location, a given start location, to a goal location, basically navigating itself in the map, in a given map, and going around the obstacles or humans, for example. So why AMR? So basically, one of the major advantages of AMR in this case would be it is highly flexible, right? So I don't need to define. So there is, yes, I do require a map for the mobile robots to move, but they're highly flexible in terms that they're able to take these decisions dynamically based on the current scenario, right? So that is what differentiates the AMR. And the AMR would then be used where there is a basically collaborative movement required with other humans, for example, or other manual entities like forklifts moving in a warehouse. Yes, and the kind of sensors that would basically be used for AMR would then be LiDAR. It could also be the safety LiDAR, the cameras, and the ultrasonic sensor for navigation and safety. Okay, so going forward, I've already mentioned some of the use cases, but quickly summarizing what would be the entire set of applications that is covered by the mobile robotics domain would first be the material transfer, right? So basically, material transfer is one major application where AMRs with different kind of attachment on the top is used, right? They are able to basically carry different kind of payload in terms of totes, cartons, or pallet. And at the same time, the amount of payload they're able to take could be ranging from very few kg, let's say 5 kg, up to very heavy loads, which 1,000 kgs of a pallet, for example. Another application, so this first application is more for the material transfer in the warehouses, basically it could be from, let's say, from the storage to the dispatch area, or from the production to the storage area. The second application where mobile robots are basically used is the human following robots. So especially in order picking warehouses, just like, for example, bigger warehouse like Amazon and Reliance, where your orders are processed before they're dispatched. So a person would therefore have to pick a lot of items from different aisles and consolidate an order. So in such cases, the current practice is to basically have a trolley which the robot would take, but the introduction of mobile robotics to this domain brings in these human following robots, which would simply follow the robot would follow the human, and the robot would follow the human and help him in this entire picking process, therefore making the picking process much more easier for the operator and a lot more efficient. The next use cases, what we have recently seen during this COVID pandemic time, is used in hospitals and office spaces. So it has been very wide. So the mobile robots have been used in hospital and office spaces for disinfection using a UV light emitter, for example, and also for serving patients or with their medicines and food in hospital spaces. Some of the other smaller application of the AMR would be the cleaning robot or the service robots, which would basically again be similar working in such office spaces or hospital spaces. So coming to the major application of the mobile robots is the sortation robot. So the above applications that I spoke about, they're more for the AMR, which is basically the autonomous mobile robot. But going forward, since AGV also captures a very big market, the kind of applications where AGVs basically are used is the sortation robots. And so in some sortation robots, the purpose of these robots is to sort thousands of items based on the destination location. So you can consider a lot of packets or a lot of items have to be sent out to a specific destination or zip code in an area. So these would have to be, for example, sorted before they're sent out. So such sorting applications, sorting robots would then basically be used in such fulfillment centers, which will sort the items. And one of the major advantages, since they're very fast, they can actually we can basically achieve a higher accuracy, efficiency, and they're very scalable. Yes, and like I mentioned, there are multiple kind of attachments that can be that can be used along with the AMR. They can be in form of a tugging operation where the AMR or an AGV simply tugs a trolley. There
Varun,
could be a
sorry to interrupt. We have a question from Professor Arpan. I think sir has raised his hand.
okay.
Yeah, hi Varun.
Yes,
Basically, Adverb is working on these problems, right?
yes, sir.
So is it vision-based robot, or the robots have some other sensors?
So basically, we both have the AMRs have camera as well as the lidar to basically localize itself in a given facility.
Okay. So yeah, so actually I am working on some problems which might be useful here, but we can discuss offline after the talk, maybe.
Great. Yeah. Okay, so quickly to summarize and basically show what these AMRs would look like. So if you first look at these order picking mobile robots, so what we see here is basically a person which has to pick a lot of particular specific items and consolidate an order. So this would be a use case where the robot could simply follow the human and help him in picking all the items for a order. And once that is completed, the robot could then go to the final dispatch area. Another application is the material movement, like I mentioned. So it is basically here the AMRs would carry certain totes or pallets on top of them, right? And would take the material in a warehouse from a storage to a dispatch area or from a production to a storage area, for example, right? Another application is the UV decimeter. So basically, it's the same AMR base which is fitted with a UV light, and it could be used for killing a lot of bacteria, viruses, which has been used recently a lot during the COVID times for disinfecting the hospital spaces and the office spaces. So these are basically the AMR categories. Now coming to more of the sortation robots. So these two, what we see here are the sortation robots. So you see, as we see here, basically these robots have a kind of
Varun,
a
we
yes,
have a
sir.
questions from uh, Dr. Atanendu.
Mhm.
Sir, please go ahead.
The question, this UV decimeter actually CD Plant has developed it long time back, and right now the person has joined with Professor Ram Prakash, who has joined with IIT Jodhpur now with Professor Shantanu Chaudhary. and they have actually given this technology to some companies, I believe in Jaipur most probably, and I can tell you exactly to whom they have given, but this is actually done by Sri Plan a long time back. Okay, maybe if you can look at those technology that they have delivered to other companies also. And the person is Dr. Ram Prakash, who is now currently at IIT Jodhpur with Professor Shantanu Chaudhary. Okay, that's the information from my side.
Perfect. Yeah, so like I was mentioning, we do have sortation robots also, where basically the idea would be to sort a particular item based on the final location where it has to go. So these sorting robots would be could be something very similar to what is shown in the image here, where they can have different attachments on the top. It could be a tilt tray, it could be a roller or a belt conveyor. And finally, they're basically, so what we see here also in image is they are guided by some kind of localization technology, which could either be a barcode as is shown in this image, or it could be some RFID tags, which help the robot know where exactly it is and where it has to travel to. Right. So these are some of the applications and use cases before I dive into a little system, what this mobile robot would be made of. Yeah, so going forward, so what we see here is a generic system architecture for mobile robots, right? So each of these mobile robot, in completeness, as in including the software and hardware, would basically be made up of a lot of sensors and other hardware. So I'll be going from lower level to the higher level, explaining what basically sits at the bottom of a robot and how they could be operated. So what we see at the bottom here is basically the sensors and the hardware. So the sensors would include something like a computing unit, which could be an industrial PC or a PC or a standard PC, where the main core algorithm would run on, right? Along with this, there will be a lot of sensors like the IMU, which help in the localization. The IMU, the 3D or the 2D or the 3D lidar, a depth camera, RGB camera. The optical flow sensors have also been used in the areas where we have seen a lot of slippage. And other sensors like the ultrasonic, for example, they find a lot of use in office spaces and hospitals where there's a lot of glass, since LiDAR and camera are not able to detect the glasses much more reliably, right? And other kind of technologies like a QR code reader would be present if a barcode, for example, on the floor has to be read to localize itself. So these are the set of sensors which would basically be sitting on a robot, right? This could be a combination of multiple sensors, or it could just be few sensors on a robot, depending upon the application and the type of the robot. So in order for the robot software to basically communicate or interact or receive data to this sensor and hardware, it would require a hardware interface layer. So this hardware interface layer ensures that there's a robust communication between the software and the hardware. And the type of interfaces could be a TCP, UDP, serial, USB, Modbus, or Ethernet IP, right? So depending upon the IO device or the PLC or any other computing unit that is present on the robot, there could be different kind of communication protocols. So in the next, we now go on to what is the robot software. So we now have the hardware, we can communicate with the hardware. But in order for the robot to actually plan its way in a given location, it would require some of these, it would require some of the modules like a map server, a localization module, a perception module, planning and control, diagnostics. So basically, I think most of them are very clear from the name itself. So the localization module would help in the localizing the robot, and the perception is more for the object detection and classification. The planning and control ensures that the paths that are made are basically smooth, obstacle free, and the map server gives the information about the static map where the robot should be moving. So most of these basically applications, what we call, would be running over a middleware. Now this middleware could be something like ROS, which is very commonly used in industry, or it could be DDS, which again is similar to ROS in terms of PubSub, publisher and subscriber technology, and could help different applications to communicate to each other, right? And finally, all this middleware and the applications would run on an operating system, which is again could be a Windows or an Ubuntu operating system. Right. So this is about the robot, but like we mentioned, since there are multiple of robots that would be running in a warehouse, they would require a fleet management system or a guidance system, which would basically cooperatively plan for all of these agents, such that the entire throughput of the warehouse or the system increases. Right. So what we see here is basically on the cloud or on the local server is a fleet management system, which would then interact with the robot and give it basically missions and commands. So I'll come to that when I go to the software architecture. But what we see here is on a local server, there are multiple of things running, such as the fleet management system. Also, we would require that the software updates basically or bug fixes are pushed to the robot. So we have over-the-air updates. The security plays a very major role. We want to ensure that the robot cannot be hacked. So basically, we have to be ensured that um, all the ports, for example, that are not used on the robot are so to say closed and so on. Other things like the simulations have to be performed. So there are a lot of simulation tools which could run over the cloud server, which could run over the cloud or the local server and help in the verification and validation of the algorithms. So I'll also come to simulations a little bit. Yes, and some of the other modules like the remote monitoring, the V2X, and so on. So this is a general architecture of how different components would be placed in a robot, going from the very low sensor level to the cloud level. I'll quickly now brief upon a little about the hardware components that would sit in a robot. So so this is one of a very generic image, basically showing what could be a communication or what are the different components that are in the robot. So starting from the center, we basically have the computing unit or a PC, which would receive data from different kind of sensors, first thing, and also from a IO device, which could be a PLC or a safety PLC. Then we have a lot of basically sensors such as the camera, the lidar, the IMU, the ultrasonic, the bumper, which is present again for the safety, be either connected directly to the computing unit, let's say over a USB cable or over a serial port. And some of these devices which are more safety, so to say, safety critical, for example, the bumper and the safety laser scanner, they would be then controlled by the safety PLC. Coming to the next is basically the environment. So each of these robots, in order to basically do its task, which is, let's say, carry load from one location to the other and transfer it from the conveyor to some external conveyor, would require some kind of a roller conveyor or a belt conveyor on the top. So the environmental interaction and attachment would basically include all the components which are required to operate a attachment. So this attachment could be, like I mentioned, it could be a tilt tray, it could be a simple hinge mechanism, it could be a roller conveyor, it could be a tugging mechanism, or it could be a hook to any shelf or attachment. Then the next is the robot chassis. So the robot chassis would basically have the motor driver, so that once the robot knows where it has to go, the computing unit along with the IO controller can generate suitable commands for the motor driver in order to drive the robot, and at the same time receive the feedback on the distance moved, the number of wheel takes, the odometry basically of the robot. And finally, one of the other components that would basically be over a network would be a virtual joystick, for example, a user interface, and a fleet management system. So these are some of the major hardware components that would be present in a robot. So any questions so far? Otherwise, I'll just move to the software one. Right.
Place of the joystick, can you also use that is brain control? That's I'm thinking, so you should be able to do that.
Yes, sir.
You're thinking, you should do that like this, and then you should also do that thing also. Joystick
exactly.
is there,
So,
but it is a manual on.
Right. It could be joystick, it could be fleet management system, or it could be any external module which which could basically be giving commands or certain tasks to the robot to move.
Okay, please go ahead.
Right. So now when I talk about the software components, so we have abstracted out, so we've understood now at this point what are the different hardware components. Now, if I jump to the software components, like I mentioned in the previous slide, the fleet management system is something that would be interfacing with the computing unit over a network module. So this is more the interface layer where the fleet management system would give certain tasks or certain actions that the robot has to do, right? So the mission manager in this case would then ensure that these actions are sort of suitably transferred to the navigation and the perception module. So let's say if the robot has to move to some location, perform some action like move the robotic arm or move the attachment. So these are handled by the mission manager, which would then tell the navigation stack and the perception stack to perform these actions. The navigation and the perception stacks would use a lot of sensor data, which is the sensor layer. It would use the information basically coming from different sensors like the wheel odometry, the IMU, the optical flow sensor, the LiDAR, to localize itself and also to find what is the optimal trajectory and the control inputs. Along with that, the safety and the diagnostic layer always ensures that all the sensors and the health of the software on the robot is healthy. Basically, the entire sensor layer is healthy. All the sensors are available. And finally, we have a communication or driver layer, which could, like I mentioned, be a lot of TCP IP or Ethernet IP or Modbus, so that I can communicate to the hardware. So this is basically a architecture of what major system components or software components would be. So now going a little into very shortly into these different software technologies. So one of the major software technologies is the navigation and the path planning. So the major goal of the navigation and the path planning algorithm is to use the data from the map, the sensor information, and the mission or the task that it gets from the fleet management system to perform them as optimally as possible. So for that, the navigation stack would basically have a global planner and a local planner, which would ensure that the paths that are taken by the robot are firstly efficient, as in their optimum paths. Shortest path, for example, could be one criteria, and they're also obstacle free. So once these obstacle free trajectories are made, they are then sent to the path tracking controller, which would ensure that the commands that are generated for the actuator are such that the robot moves on that path, right? And finally, we would have a low-level controller, which will just ensure that all these commands that are generated from the path tracking controller, they are basically within the reasonable ranges, and they're converted to the right conventional or right units, for example. So what I've listed down on the left is basically when you talk about global planner, there are different technologies like the A-star, the hybrid A-star, the Dijkstra algorithm, which helps which helps in the planning, the global planning. The local planner, again, the idea of the local planner would be to create trajectories which are obstacle free. So a lot of work has been done or is currently being done in the field of optimization based planner. MPC, for example, is one of the major areas that have been here that has been in this field for a long time. Other modules like the path smoothing, the velocity profiles, they basically ensure that the paths that are generated are always smooth. The velocity profiles are within the allowed basically within the allowed specifications, and the trajectories are always so to say smooth in terms of curvature, acceleration, and jerk. Last one important module that would fit again in the navigation is the path tracking controller, where controllers like the PID, feedback linearization, and model predictive control helps the robot to follow the trajectories as close as possible. Right. So going to the other two technologies very quickly is the sensor fusion and localization. So like I mentioned, in order for the robot to actually navigate in this area, it would require that the robot knows where itself. Right? The robot knows its location in the map, And for that, a lot of data from the ground markers, for example, it could be the barcodes or the QR codes, the wheel odometry, which is basically the information directly from the hall sensor about the number of rotations the wheel has done. The rotational and the translational acceleration and velocities from the IMU, they would go in a sensor fusion model, which would then use technologies like Kalman filter, extended Kalman filter, unscented Kalman filter, based on the model that is used to estimate the robot position and velocities. Right. One thing that goes along with it is the lidar and the lidar and the camera data. So the use of particle filters, for example, is done for fusing the lidar data and then getting an estimate not just based on the sensors like IMU, odometry, and the ground marker, but also the lidar, which is basically the SLAM methodology. Another important layer again in this domain is the safety and the obstacle detection. So modules for safety and obstacle detection ensure that the data from lidar, camera, and the ultrasonic, they are fed in order to basically detect obstacles all around the robot. So why lidar and camera both? Because lidar being in most of the applications, because of the cost being a 2D, lidar can only detect obstacles in a certain particular FOV. Camera, on the other hand, gives a much more wider FOV and is basically helping detect obstacles which might be very low to the ground, which might be even overhanging obstacles could be detected by the camera, which the lidar would fail in this case, being a 2D lidar. And lastly, like I mentioned, ultrasonics is then again in applications where there's a lot of glass involved, like the glass walls or windows where, or doors basically, where the lidar and the camera would not be able to detect. So this module together with the sensor fusion module ensures that the robot can detect all the obstacles around it and safely stop within a certain distance. And that is where, and since safety plays a very prime role, these sensors would then also have to be certified as per some standards to ensure that those safety standards are met. Okay, so quickly going on to one of the last technology, one of the major last technology that I want to focus on is the fleet management system. So we've talked about fleet management system, basically giving goals and tasks to the robot. But apart from giving the goals and the task to the robot, it is basically performing other uses, or it is basically performing other tasks as well. So one of the other tasks would be the robot and the battery manager. So robot and the battery manager. So the FMS is ensuring that that all the robots basically they are also basically at a suitable charge level, and they would ensure, and it would ensure basically whenever the battery of a robot is to fall below a certain threshold, it can actually go to charge, right? So these and apart from the battery statistics, external interfaces or external exceptions like the network delay, the network drop is then again taken care by the fleet management system. Another point is the task scheduling and the traffic management. So the fleet management not only assures, not only basically creates paths which are not colliding with each other, basically obstacle free, but at the same time, it is also ensuring that these paths have as minimum traffic as possible. And this is possible by basically the fleet management system doing the scheduling of different tasks. So task allocation ensures that the right robot gets the right task. The task scheduling ensures that these tasks are performed in a certain manner such that the traffic in the entire operation area is minimized. Right. So this is basically about task scheduling and task allocation. And the last point, what I've already mentioned before, is the cooperative path planning, where the fleet management system is planning paths for multiple of robots, such that there are no deadlocks. There's a proper wait spot, and there's an obstacle avoidance is ensured all the time. Right. So these are some of the key. These were some of the key technologies that basically constitute the robot software, or so to say, the entire robot, not just the robot, but also the fleet management system software. And a lot of challenges exist when we want to develop and also test these algorithms, right? So one of the major, one of the very useful tools, so to say, that comes very handy when we are developing such complicated algorithms is the simulation. So simulation, since it will be very difficult, um, since it becomes very difficult to test hundreds of robot in a given facility, right? Simulation plays a very powerful role in validation, basically in validation of the mobile robot algorithms. So when I talk about algorithms, they include algorithms like the navigation, obstacle detection, obstacle avoidance, path planning, and path control. At the same time, they are very useful when I want to do simulation of the fleet management system, such as I want to ensure whether the given algorithm in the fleet management system is optimum. It is able to, let's say, cover all the corner cases or the edge cases. So therein becomes simulation a very important tool. The third point being it is also very useful in designing solutions. So when I'm designing automated warehouses, then the simulation helps me to decide what is the right kind of robot, what is the right kind of operation area, beforehand, before actually deploying the solution. So therein simulation plays a very important role. And in order for the simulation to actually help us in all these activities, the simulation platform would require a lot of capabilities. So one of these very important thing is basically it should be very easy to set up and recreate scenarios. So I should be able to quickly recreate the actual scenario where the robot or any algorithm is failing. I should be able to simulate the robot as closely as possible. So I would want high fidelity sensor and robot models. So these high fidelity sensor and robot models would help to basically emulate the actual hardware as close as possible. The real-time capabilities is also equally important, but because I would want the simulation to be completed in real time or even faster than real time, so that I can basically perform multiple of tests very quickly. um, Another point is the logging and the diagnostics data become very equally important. um, the generation of synthetic data. So going forward, we have seen a lot of technologies which are basically based on machine learning and deep learning. It could be, let's say, end-to-end path planning, obstacle detection, or even so to say, control generation of the control inputs. So you basically, in order to train such models, a lot of synthetic data is required or simulation data is required, and therein the simulation basically plays a very key role to generate realistic data. And this is not just for the navigation, but also for camera, for example, image labeling, or basically having that true data is very useful for simulation plays a very key role there as well. And lastly, like you mentioned, a lot of challenges that we face in the warehouse are because of some real world disturbances. These real world disturbances could be in the form of floor not being uneven, floor not being even, as an uneven floor, network delays, blind spots. So modeling of such real world disturbances becomes also very key, very, very important when we are trying to validate all these algorithms. Um, so moving to simulation, I've listed down some of the key tools basically, which have been very commonly used in the in sort of in the robotics industry. And each of these tools basically have their own specific domain where they're very powerful. For example, something like Gazebo could be used when you want to concentrate more on the robot dynamics, right? Where we want to basically model each of the, or so to say, uh, the effect of the inertias, the effect of the weights, and the center of gravities of the robot. This is very powerful when we want to actually develop controllers, where we want to see what is the effect of the dynamics or the unmodeled dynamics. Another important application of Gazebo is basically when I want to go generate more data for a single robot, right? Since this application where we have since the application where we might have multiple of robots, becomes difficult for the gazebo to handle in terms of real-time capabilities, tools like Argos, for example, and Falcon Sim, they provide more simpler physics model for the robot. And then I can concentrate more on the applications like the fleet management system and evaluate and validate the algorithms, or maybe test the corner cases of the fleet management system. Right. So the Argos and the Falcon Sim are more related to that. And again, the Isaac Sim and the again for Falcon Sim, they provide a lot of photorealisticness, which helps me generate a lot of synthetic data for the ML and DL models. Yes, the labeling has to still be done, but at least I can quickly generate the data for these models. So yeah, so coming to some of the coming to the future development. So what I've shown is currently or what I've currently presented is most work that has been done in the industry or is currently going on. But some of the future technologies that would be very important is basically the first thing would be the visual SLAM and the mapless navigation. Why I say visual SLAM? Because going forward, we see that the cost of the LiDAR is a very big challenge. We want to have our products as cost efficient as possible. And this is possible through use of the cameras. So that is why the visual SLAM. We would definitely want efficient algorithms for the fleet management system. Since the number of robots would continue to basically increase in such a fleet, it could be as big as 500 in number. We want the fleet management algorithms to be as lean as and as efficient as possible, so that we are basically able to efficiently plan for all the robots. Other things is, like I mentioned, use of machine learning and deep learning models for path planning, control, object detection, and avoidance. And one last thing which is very important is again the scene interpretation and understanding. So I should be able to understand the environment around myself, to perceive the environment around myself with the help of sensors which are available on board. Right. So lastly, coming to the challenges that we have. So like I mentioned, most of the challenges, since these robots would basically operate in a, so to say, in a controlled environment, a lot of places or a lot of warehouses basically we face challenges deploying these robots because localization is very difficult. The warehouse continues to change, right? So there are certain obstacles in one aisle in one day, and these continue to change over time. So the localization or a robust localization in such environments become difficult. Once the localization becomes difficult, then the robot basically is not able to fulfill its goal because it has lost track of it doesn't know where it is. Second being the efficient robot fleet. So we would require fleet algorithms to be much more efficient. Um, a lot of new material and novel fabrication schemes are coming. So a lot of cost effective methods are coming up, which continuously require that the software continues to evolve itself. Cost optimization is again very important point. We want to have hardware which is as cost efficient as possible. um, AI with reasoning capabilities. Yes, we want to, going forward, we want to use the machine learning and the deep learning or AI for different applications or different tasks on the robot. But we would still want be able to basically, so to say, interpret or reason out what are the outcomes of this machine learning models, for example. And last very important challenge is, or basically one important thing, is the ease of deployment. So at the end, we would want that the entire robotic system or the fleet management system is very easy to deploy. We should be able to deploy it, so to say, very as quickly as possible. Right. So these are some of the challenges, and that basically brings me to the end of the presentation. Um, and I would like to thank you all. And if you have any questions, then would be happy to answer them.
Thank you, Varun. So we would move on to the Q&A round. So if there are questions around, people can raise their hand and we would call them up sequentially. Yes, sir. Please, Athanindu sir, please go ahead.
Varun, I'd like to ask a few questions. First of all, you at some point of time you said that is navigation and perception. But I personally feel at this stage, perception has been used a bit slightly in a loose way. In the sense, perception is, when you detect an object, or let's say you see an object, it is the higher order experience in the brain, the higher up in the nervous system, that is called perception. And it is the percept, that higher order experience is called percept. So identifying that percept is an important concept in perception. Okay, so you are doing the detection and classification, but at present, unless you have mind and consciousness, it cannot interact. That is called a strong AI. Present AI is weak AI because it cannot interact with the environment in a natural way as we human beings do. So using this term perception at this stage most probably slightly, in the not in a strong way. That is one point. And second point is the one that you have used on fleet management. What is that sphere of influence you have used? Let's say I am 100 cross 100 robots are there. Obviously, at 5 cross 5 position, we will not be able to know what is the what is there at 95 cross 95. So only it is in the neighborhood that it can see what is happening. So what is the real of influence and how does it that whole thing goes? Let's say in this respect, something like the birds, the way the birds fly on the information flows, or then the fish, a flock of fish, the way that they flow. That sort of algorithm is useful in this management.
Yes, sir. So coming to the first point that you mentioned about the perception. So yes, currently the AI what we have is basically weak, but that is where we want to go towards the what we call as the strong AI, where the robot itself is able to interpret different scenarios just by detecting different objects around it, right? So that is definitely true. Coming to the second question regarding the basically the robots. So if I understand your question correctly, and maybe to answer it, what we have is the fleet management system. The fleet management system is basically receiving the position of the robots at all the time, of all the robots. So it is able to efficiently know beforehand where the other robots are and plan basically beforehand, before even the other robots going there. Yes, if there are certain external entities which are not part of the fleet management system, for example, human movement which is not known to the forklift, then only once the agent or the human would come into the vicinity of the robot is able to take the necessary um, action to avoid it.
Okay, thank
Does
you.
that, yeah.
Thank you. So, are there any other questions from the audience?
I don't think so.
Okay.
So let us thank the speaker. So thank you, Varun, for the nice talk.
Thank you, sir.
And we have a small token of appreciation for you. So it's basically a book coupon from Springer. So Udan, can you share it on screen?
Yes, sir. Saurav? Yes. So is it visible? Yes, it's now.
Udan will follow up on this with you. So basically send you the actual coupon.
Thank you, sir.
Sorry?
Thank you, sir.
Can we
Yeah.
have a small chat after this?
Yes, sir, definitely.
So I mean, yeah. So actually, when I was listening to you, I found many of the problems that I am currently working on, or maybe I'm planning to work in near future. They match with your interest, but I'm not very sure whether you are interested in more research kind of problems or like implementation or software development.
Research is equally important, because if we at this time we do not keep up with the research, then the technologies that we continue to use will basically fall back. So
True.
research and development goes hand in hand here at Addverb. So this is one of the primary focus also.
So yeah, basically I am working on a number of problems. Maybe I can explain a little bit on each of them. So basically, um, you talked about Kalman filter and UKF.
Yeah. So.
So we are working on some problem called inverse filtering.
Mhm.
So imagine that there is a radar and a target. Okay. So the radar tries to estimate the location of the target based on the reflected signal, right? So
Mhm.
now imagine that the target wants to estimate what the radar is estimating.
Okay.
So then the problem is inverse filtering. So we are working on this inverse extended Kalman filter, inverse unscented Kalman filter, this kind of problems.
Mhm.
So, and also I think there are some problem areas that that might interest you when we can discuss about this. So basically we have got Professor Dr. Athanendu Mondal knows that. So we have got a project on radar, basically radar signal processing for cognitive radars.
Okay.
So that can be, I mean, the primary idea is we can use cognitive radars to localize objects and to track objects. So I think in robotics context, these things could be useful. Um,
Definitely. Mhm.
then also I am very much interested in, we are working on some problem on stochastic games, but I am in general interested in reinforcement learning and multi-agent